All right, guys, go ahead and if you have a calculator, you can get that out. We are going to have our third of 4 lessons in our probability little quick unit, which is probability of multiple events. Sometimes you might see this if you're trying to Google it or something, you might call it compound events. So the probability of this and then that. So I was making probably what was an inappropriate joke earlier about a parlay. Does anybody know like what that means in terms of what does that mean? I haven't heard. Are you a little deviant? Well, you can win big, but there's a reason. Yeah.
You got multiple legs.
You got multiple legs. So that just means basically you don't just need the cats to win, right? You might need the cats to win and the cards to lose or something, right? Something like that. I'm just throwing some random stuff out there, right? But anyways, both things have to happen in order for you to win, right? So the reason that's harder to do is because, and the reason you can win big is because every leg that you add, every event that you add, lessens your odds of winning, right? So that kind of concept is what we'll look at today. All right, is the more things we try to have happen, the less likely it all is to happen, right? Which I think conceptually, hopefully, kind of makes sense. Forgot I was making a video. I shouldn't have opened with the betting stuff, but oh well. It is what it is. You good?
I'm gonna go back.
Okay. All right. So probability of multiple events or probability of compound events. So there's this idea of a dependent event versus an independent event, and all this stuff we'll post on Google Classroom. So let me know if you need anything. Dependent is if one affects the other. Independent if one does not affect the other. Okay. So let's look at these generic scenarios and label them as D for dependent or I for independent. Roll a dice and spin a spinner. Okay, those things aren't related at all, so they would be independent of one another. So we'll put an I there. B, draw a card without replacing it. I would underline that phrase and draw another card. So if I draw a card and don't replace it, my sample space has changed, and therefore so that is dependent. The first thing affects the second thing. So go ahead and label C and D real quick. I'll go over those in about 10 seconds. Flip a coin, then flip a coin. Select a coin from a pike. I'm not really sure what that means, but just, think of it as a hat or something, I guess. Put it back. Select another coin. Does anybody know what that word means in this context, or do we think that's a typo? Got nothing. All right. So flip a coin, flip another coin. That would be I for independent. Okay. Select a coin, put it back. That's the key phrase there. Select again. That would also be independent. Does everybody kind of get the idea of dependent versus independent? Yes? Okay. All right. So the probability of independent events, or the probability of really any multiple events, is the probability of the first thing times the probability of the second thing. All right. Or if you add a third leg, right? The third thing, right? You can continue to multiply those probabilities together, right? And what happens when we multiply fractions together? We get smaller and smaller numbers. Okay. So let's see what that looks like. A, you are rolling a dice and then flipping a coin. So what's the probability that we get an even number and a heads, right? So we want the probability of even on the first thing times probability of heads on the second thing. So these are independent because they're different things, right? The dice roll doesn't affect the coin flip, right? So the probability of even on a number cube would be 3 out of 6, or you can write 1 out of 2. Probability of heads is 1 out of 2. Okay, when I multiply this out, I mean, this one's pretty easy. I would just reduce to 1/2 times 1/2 and get 1/4. Let me go ahead and show in the calculator how you can do that. I'll show it just so I can show it more than once. But if I wanted to take 3/6 times 1/2, one way you can type it in is just 3 divided by 6. I always like to put my fractions in parentheses. Times 1 divided by 2. There is a way to type a fraction bar. It's under like alpha, but if all you need is a decimal, you can do that. If you want to turn that decimal into a fraction, you can hit math. There, it's already on fraction. Enter, enter. Right, so 1/4. Just some cool tricks from your calculator. So 1/4 or 25%. All right, you guys go ahead and try B. This is another independent event because we have 10 diets and 5 regular Cokes, so 15 drinks. 8 bags of Doritos and 12 bags of Cheetos, so 20 bags of chips. And then we're selecting a drink and a bag of chips, so independent. Take about 30 seconds there and see if you can come up with that probability. Probability that we draw a diet, drink, and a bag of Doritos. About 10 more seconds to go over it. All right, so we would do the probability of the first thing, which is 10 out of 15, times the probability of the second thing, which is 8 out of 20. You could reduce those fractions to 2/3 and 4/5, or you could leave them as is and let your calculator handle it. Either way, my reduced fraction is 4/15, 4 out of 15, okay? Does anybody need to see any of that? How did I get 10/15 or 8/20 or the reduced fraction? Everybody okay with that? All right, moving along. So 4/15 or about 26.7%. Okay. All right, so let's look at some dependent events. The first thing affects the second thing. So it says if A and B are dependent events, then the probability of A and B is the probability of A times the probability of A, and then it has that little line in B. That means A given B. So this would be the probability of A given B. Okay, let's skip down and do B together, and I'll give you guys A. So B says you select a card from a standard deck of cards and do not replace it. This is the phrase that makes this dependent. If we don't replace it, our sample space has changed. What's the probability that we select 2 kings? In other words, what's the probability that we select a king and then a king? Okay, so probability of king times probability of king on the second draw given a king on the first draw. Okay, so does anybody remember what the probability of just drawing a king is? How many kings versus how many cards? Yes. 1/13 is correct. If you didn't know where he got that, you might put 4 out of 52. Either way, if you understand why it's 1/13, 1/13 is perfectly fine. Makes your work a little bit easier. Okay. Now, what about the probability of a king on the second draw? Does anybody want to take a stab at that? So we've drawn one, one's gone. What would the probability of the second king be? Very good. So there's only 3 kings left, right? If one's gone, and there's only 51 cards left, right? So 3 out of 51. Good job, Jade. 3 out of 51. All right, and then we just let our calculator do the work for us there. 4 out of 52 times 3 out of 51. So my percent looks like about 0.5%. Okay, let's see if it'll turn that into a fraction for me. Sometimes it won't. Okay, so 1 out of 221 is my reduced fraction. All right, anybody have any questions? All right, so you guys try I'm going to take that down to about 30 seconds there. Says, again, 10 diet, 5 regular Cokes in the cooler. You randomly select a drink and then select another drink. What's the probability that you get 2 regular Cokes? And again, it's just kind of assumed here. It doesn't say don't replace it, but if you're selecting a drink, you're not going to put it back. I guess we just assume that we don't replace it based on the context. All right, guys, that probability would be, as a reduced fraction, 2 over 21. I think that's about 9.5%. Let's see how we get there, okay? So probability of a Coke on the first draw would be 5 out of 15, or 1 out of 3. A Coke given a Coke would be 4 out of 14. Does that part make sense to everybody? All right, then we do the math, get 2 over 21. Does anybody have the decimal in front of you? Is 9.5% correct? Anybody have that? Yeah, so about 9.5%. Thanks for the help. All right, so we will keep moving along if y'all don't have any questions. All right, let's do it. So we've touched on this next thing just a bit in some of your examples, so probably teaching ahead a little bit on some of that deal. This idea of mutually exclusive events, right? So mutually exclusive events cannot happen at the same time, right? So watch out for the word or here. Let's maybe highlight that somehow. So if you see or, you gotta be careful to know what we're talking about here. You might in this lesson tend to take A plus B, A times B, but that means A plus B. So or means to add. Okay. If they're not mutually exclusive, that basically means that they can happen at the same time, and we end up, if we don't take care of that, we end up counting stuff twice. Okay, I'll show you what I mean. Okay. All right, so in example 4, students can only take 1 foreign language at a time. So that's going to be our phrase that pays there. Out of 100 students, 37 take Spanish, 15 take French. So only 1 at a time makes them mutually exclusive. Okay, so this is our mutually exclusive phrase. So that just means we want the probability of Spanish plus the probability of French, right? So so we'd have like 37 plus 15 out of the 100, right? Does that make sense? Everybody with me on that? So that would be what, 52? If we wanted to reduce, get this right, that'd be 13 out of 25. Or 52%. Okay, questions on that one? All right, let's skip example 5. I'm going to leave that one for you guys to try. Let's look down at example 6. The good old number cube. Or sorry, the good old deck of cards. You are working with a standard deck of 52. And now what's the probability of a heart or a diamond, right? So we want to add those together. So just to review, how many cards are, it says 52. So out of 52. Anybody remember how many hearts we have? Right? 13. If we have 13 hearts, how many diamonds do we have? Yes, 13, right? 13 of each suit. So 26 out of 52. Oh, also, can anybody explain why those were mutually exclusive? I kind of glossed over that. Yes. It's a heart or a diamond. And are there any cards that are both hearts and diamonds? Sorry. No, right? So that was the deal there. So you might want to mark here that these were ME. Anyways, that reduces to 1 out of 2, which is 50%. Okay, now let's look at example B. It says probability of heart of a king. That should say or. So let's just change of to or. All right, so let's go through it. Hearts, there are, we already said 13 out of 52. Okay, what about kings? How many kings are there? Anybody remember? Yeah. Okay, very good. Just 4, but then he said it'd just be 3. So let's write plus 4 because there are 4 kings. And then let's talk about why I said 3, because that's correct. Okay, these are not mutually exclusive. So let's write not ME here. Because there is such a card as a king of hearts, right? So if we don't account for that, then we've basically counted the king of hearts in this set and in this set, right? So we've counted that guy twice, right? So we got to take him away once. So this is how we're going to show that, just -1, and so that would be 16 out of 52. So that's what happens when they're not mutually exclusive. You don't want to count the repeats more than once, right? So that reduces to 4 out of 13. I don't really have room for a percent, but that'll be good enough. Any questions? All right, let's do one more together and then have you guys try just a few of them on your own there. All right, so what about example D there? Ace or a black card, okay? So 4 aces plus how many black cards? We haven't discussed that yet. Yes, 26, right? So two of the four suits are black. The other 2 are red. Okay. So 13 and 13 gives me 26 black cards, right? Now we got to take away any that might happen to be both. Are there any black aces? Yes, there are. There are 2. That's exactly right. So again, this is not ME. So we're going to take away, like Jade said, there are 2 of them. You got an ace of spades and an ace of clubs. Okay. So 28 out of 52. Does that sound right? 28 out of 52 or 7 out of 13. All right. So we have left example 5 blank, and then we've left 6C blank. Do them in whatever order you want. We'll go over the answers to those 3 in about a minute. You don't have to get them all done. This is where you guys can collaborate a little bit, talk to each other, and that'll be our lesson. All right. The probability of we'll just go in order. So if you got to 5A, if you worked your way upwards, you may not have. But for anybody who did, feel free to jot this down as well. In example 5, we're rolling a dice, rolling a die. So 2 or 3, that'd be 1, 2 plus 1, 3 out of 6 options, which would be 2 out of 6 or 1 out of 3. You got to be careful with this too, right? Because notice the subtle difference between or and, right? And would indicate we get a 2 and then a 3, doing 2 things, right? Or means one roll of the dice, what's the probability we get either one of these? Okay, so a little subtle difference could cause you some issues. B, even or greater than 3. So this would be, there are 3 evens. There are 3 numbers that are greater than 3. Then you think, are there any that we counted twice? How many? Anybody know? Yeah? We counted 2 twice, right? Because 4 and 6 are in both sets, right? So hopefully that's making sense. So when it's all said and done, we have 4 out of 6, or 2. That covers 2/3. Everybody with me? All right. Then the last one, if you got there, depending on which order you went, ace or king. First of all, this is mutually exclusive because there are no repeated aces or kings. So we just do 4 aces plus 4 kings out of 52, and that's 8 out of 52, which reduces to 2 out of 13. Anybody need to spend any more time on those? All right, guys, so be careful when you're doing your homework. Hopefully I got them both in there. If not, I don't know. Might have to revisit it. But if they're, and versus or, that's kind of a big difference.